I'd like to continue the discussion about rockets today and go into some details of rocketry. Before that, I want to briefly mention that there was work done in the mid-20th century to develop airplanes that could go to space. In the 1950s and 1960s, airplanes were more developed as a means of transporting people than were rockets, so it wasn't crazy to think that more powerful airplanes would be the vehicles that took humans to space. I'd like to discuss one airplane in particular. This is the X-15 airplane. The X is for experimental, and it still to this day holds the record for the fastest crewed airplane flight. During one flight in 1967, William Knight flew at Mach 6.7, which is nearly 7 times as fast as sound speed. This is about 7,200 kilometers per hour, or 4,500 miles per hour. Also, two X-15 flights, Flight 90 and 91, got above the Kármán line at 100 kilometers, or 62 miles, above sea level. Both flights were piloted by Joseph Walker. This technically made Joseph Walker an astronaut since he was above the altitude that is generally considered space. Note that Earth's atmosphere doesn't abruptly end as you go up from the surface of the Earth. It gradually becomes less dense to the point that airplanes find it difficult to generate lift since there isn't enough air flowing over their wings. As such, the Kármán line is approximately the altitude at which an airplane would need to go as fast as an orbiting spacecraft to generate enough lift to fly. This video shows the X-15 flying. It was taken to an altitude of about 13.7 kilometers or 8.5 miles by a B-52 mothership and then was released while already traveling at about 800 kilometers an hour or 500 miles an hour. One famous test pilot of the X-15 airplane was Neil Armstrong, who went on to be the first human to walk on the moon. Last time we saw two end members of rockets, solid-fueled rockets and liquid-fueled rockets. The Apollo program largely uses liquid-fueled rockets, so I'll be focusing on those today. Liquid-fueled rockets can be further divided into monopropellant and bipropellant rockets. We have seen a few examples of bipropellant rockets. As the name implies, these rockets, like the one shown in the diagram, have two propellants, an oxidizer and a fuel. A monopropellant only has one propellant. For example, hydrazine, N2H4, can be used as a monopropellant. We saw last time that while solid fuel rockets are relatively simple in design, they're generally not as powerful as liquid fuel rockets. Also, liquid fuel rockets have the ability to be stopped during a mission and restarted when needed. You may recall that the Saturn V's third stage needed to do this to get into Earth orbit and then leave towards the moon. We also talked about how it's difficult to make sure that propellants are going into the combustion chamber at the necessary rate when the tanks are moving with the rocket. As propellants slosh around the tanks, a mechanism is needed to push the propellants through the pipes. There are two main ways to force the propellants into the combustion chamber. One kind are pressurized systems and the other kind are turbopump systems. Let's first look at pressurized systems. Pressurized systems are also called pressure-fed cycle engines. Shown on the right is a schematic of this type of propulsion system. The fuel tank and oxidizer tank combination that feeds to a combustion chamber is likely familiar to you by now. However, this system has an additional tank with a pressurized gas. This gas is taken from the tank and heated by the combustion chamber. It then is fed to both the fuel and oxidizer tanks to force those propellants down into the combustion chamber. While this system is relatively simple, it does add weight due to the extra tank of pressurized gas. In rocketry, you want to reduce the mass of the rocket as much as possible. Another thing is that you need to have the pressurized gas at a very high pressure to ensure that as time progresses, there is enough pressure towards the end to keep pushing the propellant through the pipes. A famous example of a pressure-fed cycle engine was the one used on the Apollo spacecraft. They used a type of hydrazine, N2H4, as fuel and nitrogen tetroxide, N2O4, as oxidizer. Recall these propellants are hypergolic, meaning that they ignite upon contact. By the way, hydrazine is highly toxic, so a lot of care needs to be taken since it potentially can cause cancer. Now let's take a look at turbopump systems. Turbo is short for turbine. A turbine is a fan-like device that converts linear fluid motion into rotational motion that can be used for doing work. In the case of a car turbo, it is used for adding more air into the engine to get more power. A famous turbopump system was the F1 engines of the Saturn V as shown on the left. There are different types of turbopump systems, and the F1 engines were of the gas generator cycle type. Shown on the right is a schematic of a gas gas generator cycle engine. As we have seen already with liquid fuel rockets, the main idea is to get fuel and oxidizer to the combustion chamber. Recall that for the F1 engines, the fuel was rocket propellant 1, or RP1, and the oxidizer was liquid oxygen. Let's start with the pre-burner. It's conveniently named since it ignites a little quantity of fuel and oxidizer to make hot exhaust. That hot gas is fed to the turbine, which makes the turbine spin. The spinning of the turbine operates the pumps of each of the propellants, helping the liquids flow down to the engine, or engines in the case of the Saturn V's first stage. You may notice though that there is something odd with the fuel line in this diagram. While the oxidizer line feeds directly into the combustion chamber, the fuel line goes past the combustion chamber and wraps around the engine's nozzle, or the bell-shaped part, a few times before being directed into the combustion chamber. Why do you think that is? One reason is that they use the fuel to cool the extremely hot engine nozzle. We will see typical temperatures in a moment. So the fuel, which may be very cold to start, acts as a coolant, much like the case of radiator fluid in a car, that helps cool the car's engine. Another reason for wrapping the fuel line around the engine nozzle is to heat up the fuel. Combustion is most efficient when fluids are in a fine vapor state. You may wonder how exactly F1 engines on the Saturn V were started. Even though the actual propellants were rocket propellant 1 and liquid oxygen, the starting of the engine was done using hypergolic propellant. Remember that hypergolic propellants ignite on contact, so they are a convenient choice. Not all liquid-fueled rocket engines are started using hypergolic propellants. Here is a main engine from the space shuttle, which used liquid hydrogen as the fuel and liquid oxygen as the oxidizer. This is a smaller engine compared to the F1 engine, and the space shuttle had 3 of these. These engines were started using spark plugs much like car engines, so an electric spark ignited the liquid hydrogen and oxygen. I took a picture of a nice graphic at the Kennedy Space Center that shows various temperatures for reference. Celsius is on the bottom and Fahrenheit is on the top. Take a look at where the average human body temperature is on this figure at about 100 degrees Fahrenheit or 37 degrees Celsius. Fireworks are about 2,500 degrees Fahrenheit or 1,371 degrees Celsius. And quartz sand turns to glass at 4,172 degrees Fahrenheit or 2,300 degrees Celsius. Notice that inside the engine, meaning the space shuttle main engine, was at 6,000 degrees Fahrenheit or about 3,300 degrees Celsius. This is well above the temperature at which copper boils. Now I would like you to either read or listen to the communications leading up to the launch of Apollo 11. Often documentaries of the Apollo program speed up this moment, but I would like you to take in all the events that are going on leading up to the launch. You'll mostly be reading or hearing from NASA's Public Affairs Officer Jack King.
T-minus 1 minute, 35 seconds on the Apollo mission, the flight to land of the first men on the moon. All indications coming in to the control center at this time indicate we are go. 1 minute, 25 seconds and counting. Our status board indicates the third stage completely pressurized. 80-second mark has now been passed. We'll go on full internal power at the 50-second mark in the countdown. Guidance system goes on internal at 17 seconds, leading up to the ignition sequence at 8.9 seconds. We're approaching the 60-second mark on the Apollo 11 mission. T-minus 60 seconds and counting. We passed T-minus 60. 55 seconds and counting. Neil Armstrong just reported back. It's been a real smooth countdown. We passed the 50-second mark. Power transfer is complete. We're on internal power with the launch vehicle at this time. 40 seconds away from the Apollo 11 liftoff. All the second stage tanks now pressurized. 35 seconds and counting. We are still go with Apollo 11. 30 seconds and counting. Astronauts report it feels good. T-minus 25 seconds. 20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
We got a roll program.
Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading.
One thing that you would have noticed is that ignition sequence start is set at about T-minus 9 seconds. It takes the 5 F1 engines a few seconds to get going at full throttle. You can't just turn on the Saturn V and just go. Also, you may have noticed how they have liftoff, but then it takes a few seconds for the Saturn V to clear the tower, meaning that the bottom of the rocket went past the top of the tower. While the F1 engines were very powerful, the Saturn V was also very heavy. This was why the Saturn V didn't just shoot off. It almost crawled vertically into the sky at first. So the engine started a few seconds earlier than launch. In this plot, the time of launch is marked as 0 in the horizontal axis. Both vertical axes on the left and on the right are showing thrust in different units. The exact numbers are not important. The main point here is to realize how the engines were gradually building up thrust before liftoff. The Saturn V's computer was programmed to check that all 5 engines were running at their intended thrust levels before it launched. Also notice here that engine 5, the center engine of the 5 F1 engines, came on first. Then the other 4 engines came on in opposing pairs. This was a balance issue. Turning on engines on opposite sides made sure that the whole Saturn V didn't fall over. Now let's take a look at accelerations experienced by astronauts during liftoff. The horizontal axis shows time in seconds since liftoff, and the vertical axes show accelerations in either standard units or g-force. Using g-force is nice because one means what you are experiencing right now under the influence of Earth's gravity. Feeling 2 g's would mean feeling like you were twice as heavy than you are currently. Apollo astronauts experienced a maximum of 4 Gs, meaning that they would have felt as if they were 4 times as heavy than they were on their seats before launch. The different colored boxes in the figure divide the timeline into the 3 stages of the Saturn V rocket. The number 1 indicates liftoff, and the acceleration builds up rather quickly due to the power of the Saturn V's first stage. Number 2 is the point when the center engine of the first stage cut off. Recall, that's the engine that started first. The acceleration dropped due to the cutoff and then started to build back up until all 4 remaining engines of the first stage cut off. The g-force went to 0 as astronauts would have experienced a moment of weightlessness, much like you experience on a roller coaster or an airplane flying through turbulent air. Number 4 is the starting point of the second stage burn. Again, the acceleration builds up to the point of center engine cutoff. You'll notice that there is an extra bump in the acceleration for the second stage. This is due to the changing of the amount of fuel and oxidizer used. They changed the fuel-oxidizer ratio to improve efficiency of the burn to save propellant for the relatively longer burn of the second stage. After the remaining 4 engines cut off, astronauts would have again felt near weightlessness. Number 8 is the start of the third stage, which burned for a short time to get the astronauts into orbit around the Earth. In a little over 10 minutes, the 3 Apollo astronauts were in space. Now I'd like to talk about Pogo oscillations, which rockets experience during launch. It's a negative effect that needs to be worked out, otherwise it can lead to the destruction of the rocket. It is named after the Pogo stick, which is shown on the left. I would like to show an example of the Tacoma Narrows Bridge, which was a bridge in the state of Washington in 1940. It is not a perfect example to demonstrate pogo-like oscillations, since those have more to do with structures shaking at their natural or resonant frequencies. The breaking glass using sound example that is often done in science or physics classes is a better demonstration of what pogo-like oscillations can do to solid objects. Yet, I think the Tacoma Narrows Bridge is a dramatic example of how seemingly solid structures like bridges can be bent, twisted, and broken by the motion of fluids like the wind. On the day of the bridge's collapse, it was only 4 months old. The video shows the bridge swinging erratically while there is one person left on the bridge. Leonard Coatsworth was trying to get his daughter's dog out of the car. The dog, being scared, would not leave the car. Leonard finally had to leave the dog. He barely made it back to safety himself. Going back to rockets, pogo oscillations are oscillations in the structure of rockets. The structure of the rocket starts to vertically stretch and compress like an accordion. It is caused by combustion instabilities in the rocket's engines and may lead to the breakup of the rocket. This effect was studied heavily during the Gemini program when Titan II rockets were experiencing too much pogo oscillations for use by Gemini astronauts. Pogo oscillations were experienced by the uncrewed Apollo 6 mission, but the mission wasn't significantly affected. The crewed Apollo 13 mission experienced pogo oscillations when their second stage was burning. By the time of Apollo 13, they had programmed the Saturn V's computer to shut off any erratic engine, so the computer decided to shut off the center engine. It didn't affect the mission in getting into orbit since they just burned the remaining 4 engines of the second stage for longer to get the necessary altitude and speed that they needed. Of course, Apollo 13 would would go on to have many other problems, but fortunately it wasn't affected too much by Pogo oscillations. Things like Pogo oscillations are what makes rocket science rocket science. It's not easy because there are many things that could go wrong, and it's difficult to predict what those will be 100% of the time. We have of course learned a lot over the past several decades, but it's a constant learning experience, and it's utterly foolish to be nonchalant when dealing with rockets.